We're at the end of our partial fractions journey here. Part 4. So far, we've looked at linear factors, okay? Some repeated linear factors. Now we got to consider some of these extra special cases. What happens if I have an irreducible quadratic? And the weirder cases, too. What happens if I just have some ordinary rational function and it doesn't look like I need to do partial fractions? We'll see what that looks like. So let's start here. I got this integral from 0 to 1, x over x squared plus x plus 1. You know, I'm doing this in my head and I don't think I can factor the denominator in terms of real numbers, okay? So I'll show you that we can't do that, okay? So let's take a little side excursion here and look at the quadratic formula here. Well, let's find the zeros of the denominator. So if I try to find the zeros of the denominator here, okay, so let's say we use the quadratic formula. So negative b plus minus square root of b squared minus 4 times a times c all over 2a. We get, look at that. Trying to take the square root of a negative number. That gives me some complex numbers. Negative 1 plus minus I square root of 3 over 2. See, my roots of the denominator are complex. They're not real. So I can't factor this over to real numbers. So this guy here is an irreducible quadratic. Okay, it's an irreducible quadratic because the roots that we got out of here, these are complex. These are complex roots, okay? Remember that the square root of minus 1 is I, okay? If you don't remember that, that's okay. But we have complex roots here, so this is irreducible. So what do? Well, I'll spoil it for you. We don't actually have to do partial fractions on this one. Okay, this is showing you that just because you have a rational function doesn't necessarily mean you have to do partial fractions, okay? So this is one case where we don't have to do partial fractions. So what do? Instead, we complete the square, all right? So we complete the square instead. Complete the square. Fix that. Okay, so again, I did this in the trig integrals, the trig substitution video. In the advanced examples, there were a couple where I had to complete the square, and some of those, you know, didn't look too friendly, but what a bit of work, you got it. Okay, you can watch how to complete the square in your favorite algebra text. Okay, I also have a couple of videos on how to do completing the square. So now to complete the square here, we're going to do this here. We have x squared plus x plus 1. I want to write this so that I have these first 3 terms here make up a complete square, so I can factor it as x plus or minus something squared. Well, remember the method, right? We take half the linear term and we square it. So what we do is we're going to add a half of 1 is, well, a half. Then square that, that's a fourth. We're going to add a fourth here. And then we're going to subtract a fourth here. Okay, remember, that's to keep the balance. Okay. Now, that stuff in the blue under bracket factors as x plus 1/2 squared. And then what about the rest? Well, 1 minus a fourth is 3/4. Now, doesn't that look like something we may have seen before? Something squared plus number squared? I see that, so I should say, hey, that's a trig sub. So we're going to go ahead and do a trig sub here. We're going to set x plus 1/2 equal to, well, what? Well, I'm going to use a tangent substitution since it's a sum of squares. So I'll write this as tangent y here. Okay, I don't want to use theta. It's going to look a little sloppy. But what do I choose for my a? Remember, for my a, okay, let's do this here. A, we take the square root of the number that we're adding there. Well, that's just the square root of 3 over 2. So a is the square root of 3 over 2. So x plus 1/2 is square root of 3 over 2 tangent y. And so that means dx is equal to square root of 3 over 2 times secant square y dy. Okay, now we just have to change the limits of integration. Okay, remember, anytime we do a change of variables, I have to change the limits of integration. We're changing units. So I'm going to do this in, I guess, orange. Okay, there's a lot going on here. So when x is equal to 0, okay, I have 1/2 equals square root 3 over 2 tangent y. I need to solve for y. Okay, which angle satisfies this equation? Okay, I'll spare the details. Okay, but when you do that, okay, we get that here y is equal to, I wrote it down here, pi over 6. Okay, so let me talk through that. We multiply both sides by 2, divide by the square root of 3, take the arctan, okay, and the arctan of 1 over square root 3 is pi over 6. Okay, you're solving for tangent y here. Okay, here you should use your unit circle. Let's make another note here. Okay, so this whole block here, unit circle. All right, now for x equals 1, okay, something similar. 1 plus 1/2, we plug that into our substitution up there. So 1 plus 1/2 is 3 over 2 equals square root of 3 over 2 tangent of y. So that means y, when we do the work here, I'll spare the details. Okay, that's for you. Y is pi over 3. So now we just got a crazy integral to deal with here. Let's go ahead and write everything down. So our integral has transformed. Let's write down the original one again. 0 to 1. Okay. X squared plus x plus 1 in the denominator and an x on top. All right, so we got a lot of things going on here. The new integral is 1 from pi over 6 to pi over 3. But what do we do with that lone x on top, okay? Well, remember from our substitution, we can go ahead and manipulate that. So if I just push the 1/2 somewhere else, namely the right-hand side, okay, we get that x is equal to square root of 3 over 2 tangent y minus 1/2. Okay, we just put that in there. So square root of 3 over 2 tangent of y minus 1/2. And then on the bottom, okay, I'm going to go ahead and use the thing I'm going to box here in this green. Okay, I'll go ahead and skirt the steps here a little bit. Okay, just go back and watch the trig sub video if you need to refresh on how to handle this. But x plus 1/2 is square root 3 over 2 tangent y. Okay, so yeah, let's just go ahead and do it for kicks here. So square root 3 over 2 tangent of y squared plus 3 over 4. Okay, and then dx is, well, let's see, square root of 3 over 2 secant square y dy. All right, so we're getting somewhere. And where's my cursor? There it is. And I still have plenty of page here. Okay, there's going to be a lot going on here. First off, this square root of 3 over 2 that I'm going to highlight in magenta. Okay, that square root of 3 over 2, that's a constant, so I can go ahead and just shove that outside. So I have a square root of 3 over 2. Ugh. Uh-oh. Oops. Square root of 3 over 2 times this integral. Okay, now let's see what happens here, okay? Numerator stays the same. And on the denominator, okay, I get a 3/4. Okay, square root of 3 over 2 squared is 3/4. And I'm going to factor that out. We have a tangent square y plus 1 secant square y dy. Okay, now again, for this part here that I'm underlining, highlighting in green, okay, go from here to here. Okay, go ahead and square the first bit in the parentheses. So square root of 3 over 2 squared, that's 3 over 4. And you see that you have a common factor of 3 over 4. You can factor that out. Okay, and then you have 1 plus tangent squared, which is secant squared. So 1 plus tangent squared is secant squared. Okay, those vanish. And now what I'm going to do, okay, I have square root 3 over 2 times, well, that 3 over 4 I can push out. But remember, that's 1 over 3 over 4. okay? So I can go ahead and flip, okay? Dividing fractions, right? Multiply by the reciprocal. So 4 over 3 times this integral. And so what do we really have left here? Well, I have square root of 3 over 2 tangent of y minus 1/2 dy. Okay. So the second part of this, the minus 1/2 in the integrand, that's easy, right? Minus 1/2 y. But when we integrate tangent, okay, this is going to be a base integral that we should remember. And in fact, you can get this from u substitution. So I'll just write this down here. The integral of tangent of y, because we'll use this here, it's minus log of absolute cosine of y plus a constant. Do a u sub here, okay? You're going to write tangent as sine over cosine. Okay, this is a result that's derived in a lot of texts, but you're just going to write tangent as sine over cosine, and then you use a u substitution. So I'm just going to go ahead and use that here. So, oh boy, there's a lot to go on here. Let's write this here. So the scalar is out front, okay? 4 over 2, that's just a 2. So I have 2 square root of 3 over 3 times square root of 3 over 2. Well, there should be a minus sign there, okay? So negative log of absolute cosine of y minus 1/2 y. I'm going to evaluate this between pi over 3, pi over 3, and pi over 6, okay? There's gonna be some stuff here, okay? So just, work your way through, all right? And how do we handle this? Well, that scale factor is just going to be there. Did I miss something? Yeah, I did. So I'm missing a, let's see, minus square root of 3. So minus square root of 3 over 2 times natural log of that stuff, okay? Now you just gotta write everything down. Okay, just be very careful about it. So I'll just show these evaluations here. So we have plugging in pi over 3, okay? Log of, well, what's the cosine of pi over 3? Again, use your unit circle. The cosine of pi over 3 is 1/2. Yes, okay. Cosine of pi over 3 is 1/2. Okay, and then I have minus, okay, half of pi over 3, so I'll get a pi over 6. And then minus, all right, we do the same thing, but this time with pi over 6. So minus square root of 3 over 2 times log of the cosine of pi over 6. Well, that is square root of 3 over 2. Unit circle once again. And then when I plug in pi over 6 for y in the second bit, I get a pi over 12. Okay, let's do some tidying up here. Oh boy. So 2 square root 3 over 3. Now, I see I have a negative. Let's write that in this color. Minus pi over 6, and then minus a minus pi over 12. Minus is plus. All right, so minus pi over 6 plus pi over 12 gives me, well, it gives me a minus, minus pi over 12. Okay, and then the logarithms, we're just going to go ahead and shuffle with the signs here. So, and in fact, what I'll do is, well, let's just write it down first. So square root of 3 over 2, log of square root of 3 over 2, and then minus square root of 3 over 2, oh boy, log of 1/2. Okay. And I can keep cleaning up here. Let me give myself a bit more room here. Oh, we're at the end of the page, basically. All right. So if you do the work here, okay, well, that shouldn't be too bad here. So I'll have a minus pi over 12. Minus pi over 12 in the front there. But for those two logarithms, okay, I can factor out some stuff and do some other things with log properties and the like. You will see that we get a, well, let's see here. What did I write down? We'll have a square root 3 over 2 times log of square root 3 over 2 minus log of 1/2. Okay. That closes there. Bracket. Okay, and if you do a bit of extra work, okay, I don't really expect anyone to really go this far. You can leave it like this. But the cleanest way this shows up is half of log 3 minus I squared root of 3 over 18. Wow. But what was the punchline here, okay? Let's just focus on looking at like the antiderivative, okay? The punchline is, remember, just because there's a fraction there doesn't necessarily mean you have to use partial fractions. Okay, here I had to complete the square, and then this reduced to a tangent substitution, and, you know, same sort of game. Yeah, there was a lot of like logs and stuff floating around, but hey, it came out relatively nicely. All right, that probably was a crazy one to start out with. Let's look at something like this one. Oh, okay, this looks a little more familiar. Oh, thank goodness. Okay, so I wanted to look at this integral here. X squared minus 2x minus 1 over x minus 1 squared times x squared plus 1. So this one's already factored, and yes, I can use the method. Okay, so first, the recipe. So I'm going to write this here. Okay, notice that I have repeated linear factors and an irreducible quadratic. Okay, those sums of squares, whoops. Those sums of squares, x squared plus 1 and the like, will always give you an irreducible quadratic. So our recipe says it should be a over x minus 1 plus b over x minus 1 square. And then plus, well, with the x squared plus 1 there, I need to have a cx plus d, okay? The numerator here is at worst linear. Okay, there's my recipe. Now we apply the method. Okay, so now we figure out what the weights A, B, C, and D needs to be. Usual stuff, go ahead and multiply through. So x squared minus 2x minus 1 equals, well, let's see here. Okay, I'll have A times x minus 1. Again, I encourage you to write out the multiplications and everything. Okay, plus, whoops. Okay, don't forget the x squared plus 1 here. Okay, plus b times x squared plus 1. Okay, and now plus cx plus d, oh boy, times x minus 1. All right, now it's just time to use our favorite methods here. So I would probably go ahead and just use the lazy cover-up method here, okay? So if x is equal to 1, okay, if we do a cover-up method here, well, on the left, 1 squared is 1, minus 2 is negative 1, okay, minus 1 is negative 2. So on the left, we get negative 2, and on the right, well, let's see. So if we're plugging in x equals 1, everything with a 1 and x minus 1 will vanish. So the a vanishes, the c and the d vanish at the same time, thankfully, okay? So we just have, what, x squared plus 1, so 1 squared plus 1, that's 2, to be, or not to be. That is the question, and the answer is b is equal to minus 1, okay? Solve for b there, simple. All right, now we gotta be a little more clever here. This is where things can really get, shall I say, annoying. We've kind of run out of things to use. I could, you know, be a little cheeky and plug in, say, x equals I, x equals minus I, but let's keep everything in the real numbers here. I'm gonna go ahead and plug in x equals 0 and see what happens here. So on the left, I'll get negative 1. On the right, well, let's see. I have negative 1 times 1, which is a negative 1, so negative a. And then I have, well, b, so plus b. And let's see, what happens here? I'll get cx plus d times x minus 1. Well, c times 0 is 0. Okay, and then I get a negative 1 for the d term there. Okay, but remember, I know what b is, so I can just plug that in. So let's look at what the equation results here. We get negative 1 equals negative a plus b, which is negative 1, minus d. I can add 1 on both sides, okay? So I get, let's see, negative a, negative a plus d equals 0. Okay, so that's one equation. Doesn't really get me anywhere, does it? Well, we just got to keep working at it, okay? Choose some more clever values, okay? And you'll get a system of equations, okay? Maybe we can use this to our advantage. Okay, so we use x equals 1 and x equals 0. Let's go ahead and use x equals -1. Okay, so plugging that in, I get 1 minus 1, which is 0, and then I get a 2 for the other term. Okay, and now let's see what else I get. So -2a. Well, when we plug everything in here, so let's see. -1 squared is 1, plus 1 is 2. -1 minus 1 is -2. Times a positive 2 is a -4. Okay, so there's my a term. My b term, okay, -1 squared is 1 plus 1 is 2. And then 2 times b, well, b is -1. So go ahead and replace that there. Okay. Now we have this here. So I'll have let's just write it like this. -1 minus 1 is -2 times cx plus d. Well, x is -1, so that's going to be -c plus d. Let's do some tidying up here. Okay. So if I add 2 to both sides and distribute, okay, so I get 4 equals -4a. And let's see here, plus 2c minus 2d equals, well, that equals 4. Okay, well, we're going to have to get another equation because I have 3 unknowns there, a, c, and d. Okay, this is how partial fractions can be a little annoying. Okay. I'll go ahead and choose x equals 2 here as our last one. Okay, we really don't have any other cool options here. Again, if you're clever, you can use complex numbers. So if I plug in x equals 2 on the left, 4 minus 4 is 0. And then 0 minus 1 is -1. And let's just see what happens on the right, okay? So plug in 2, I get 1. And then 2 squared plus 1, that's 5. So I get 5a. Okay. Plus, well, minus, because b is -1. So 2 squared plus 1, that's 5. So minus 5b, so minus 5. Okay, and now we just got to deal with this. So 2 minus 1 is 1. So, okay. And then plus 2c plus d. When we clean this up, what do we get here? So add 5 to both sides. We get 4 is equal to 5a plus 2c plus d. Okay, so we have 3 equations and 3 unknowns. Okay, you're gonna have to use some methods here to solve this. Perhaps substitution works out. In fact, if you look here at the first equation, okay, in the first equation here, this -a plus d equals 0, this one immediately tells us that a is equal to d if we just shuffle some things over, right? And so what I can do now is just turn everything into 2 equations, 2 unknowns. So let's do that. I hope I still have room here. Okay, I still got room. That's good. So let me go ahead and indicate what I'm going to do here. I'm going to go ahead and replace all my D's with A's, okay? Plus, because my capital D's are kind of looking kind of sloppy. So I'll have -4a. Okay. Well, a is equal to d, and I'm going to replace d with a. -4a minus 2a is -6a. Plus 2c equals 4. In the second equation, 5a plus a, because d is equal to a, that's 6a, plus 2c equals 4. Okay, I know how to do this. All right, I'm in my comfort. I can eliminate, so I can add here. Okay. The a's will vanish because -6a plus 6a is 0. 2c plus 2c is 4c equals 4 plus 4. That's 8. And c is, yes, 2. Okay. C is equal to 2. Now what? Now we take that, plug it into one of the equations. We can easily solve for the other variable. Okay, so I'll go ahead and kind of getting a little sloppy here. So let's plug it into the second equation. 6a plus 2 times 2 equals 4. So 6a plus 4 equals 4. Something funny happens here. Take a look here. 6a equals, well, 4 minus 4 is 0. So a is 0. And d is 0. Why? Because a is equal to d. Well, let's take a look here, okay? A and d are 0. Okay, sure. And we have values for b and c. All right, I don't want to write the integral again, so we're going to be lazy and lasso. And now that we use the method to get our weights, all right. Oh, I'm so glad we were... That was a lot of algebra, but that's what this is, right? No calculus for that part. All right, now comes the calculus part. This guy, dx, is equal to the integral of, well, a is 0, so that's gone. D is 0, so that's gone. Okay, C is equal to, and what do we say C was? C was 2. 2x. And B was, wow, B was all the way up there, right? B is equal to minus 1. We got C is equal to 2. A is 0. D is 0. Man, what a lot of work. Okay, so C is equal to 2. Oh, no, sorry. B is what I wanted. I pinched in. Okay. You can see my bad handwriting in high resolution. B is -1. Okay. All right. We're almost done. Okay, just do a bit of tidying up here. That there. Put a dx. Okay, these two integrals are not that bad. Okay, so the first one. All right, it's power rule, right? Think about that as x minus 1 to the minus 2. Okay, when you do that, okay, when you use the power rule, well, we'll have a -1. Let's just write it out. -1 times x minus 1 to the minus 1 over a minus 1 plus, well, there are two ways you can handle this second integral. I see a sum of squares on the bottom. That's a tangent substitution, but some of you may be thinking arctan. Not quite. Do a use up. Do a basic use up here. I'll show you. Check it out. This integral here, we will let u equal x squared plus 1. Du is equal to 2x dx. And what does that reduce to? I'm just integrating 1 over u. And what integral is that? Log of absolute u plus a constant. That's easy. Holy cow, that was easy. All right. So log of absolute x squared plus 1 plus a constant, because remember, u was x squared plus 1. Okay. And let's go ahead and tidy up this last one here. Well, -1s drop out, and I have 1 over x minus 1 plus a natural log of x squared plus 1 plus a constant. And we're done. Sean, you should have wrote absolute values there. Yeah, but notice that 1 plus x squared is always positive, so its absolute value is equal to itself. Okay, if you know that the inside of your thing is always positive, okay, then you don't have to write the absolute values down. But, you know, it's also good to keep kosher. If you want to keep kosher and write it with the absolute values, go ahead. Okay, that was probably a good thing to do. But take a look at this. Where was the only calculus? Just right there. This was the only calculus here. This was just all algebra, okay? Write the recipe. Use the method. Might take some time. Take a look. I got something nice here, okay? Two more. Now let's look at this integral here. X squared plus 1 over x squared minus x. Now, partial fractions can only be done if your, let's see here. Partial fractions can only be done if your rational function is bottom heavy, okay? Bottom heavy means that the degree on the bottom is bigger than the degree on the top. And remember that the degree of a polynomial is the highest power that appears, the highest exponent that appears. So degree on top here, I'll call this degree of p. This is 2. And the degree of the denominator is also 2. So what happens now? Do we just give up? Well, no. No, we can still do something here. We have to use polynomial long division. So if it's not bottom heavy, we use long division. There we go. Long division. What? Okay. So I'll explain how the long division algorithm works here, okay? It looks like the same kind of long division you did in like the 4th or 5th grade. We're just going to extend this to polynomials, okay? So I'm going to go ahead and do the long division. So x squared plus 1, but to keep things clear, I'm going to leave a space here for the linear term here. I'll write a 0x there. I'm going to divide that by x squared minus x, okay? So that's my divisor. Now, the way polynomial long division works is similar to the way that it works for, integers, like you learned in 4th, 5th, or 6th grade. So how does that work? So what we'll do here is we're only going to consider the highest degree things here. And we ask ourselves, well, what is x squared divided by x squared? Well, it's 1, right? Okay, we divide with exponents, I subtract the powers. X squared divided by x squared is 1. So I put a 1 here, okay, in that slot. And now I do the usual multiply, okay, the usual multiply step, okay? 1 times x squared is x squared. And then 1 times negative x is negative x. And now I'm going to subtract, right? Just like with integers, right? Just like the old days, okay? So we subtract. And I always like to put the parentheses there just so I don't accidentally mess something up. Okay, just to remind myself that I'm subtracting. So x squared minus x squared is 0. 0 plus x is minus negative x. 0 plus x is x. Then 1 minus 0 is 1. And notice that the degree of that leftover stuff is smaller than the degree of my divisor. That means I'm done. So how do we read this off, okay? Well, this 1 here at the top here, this is your quotient. And then this x plus 1 is the remainder. Now, of course, if you had more terms to go through, then you keep going, follow the process, look at the highest degree term until, you get to the end, something like this. There are examples in the textbook, in the OpenStax Pre-Calculus, and the OpenStax College Algebra. I really encourage you all to look at that just to look at how polynomial long division works. Okay. So the way we're going to write this, okay? So our original integrand was this. But now I have my quotient, so that just gets its own part, so it's 1. And then I have plus the remainder, okay? The remainder, it's going to be the fractional part, okay? So the remainder bit, x plus 1, over the divisor. And I'm just going to go ahead, actually, let's not do that. Now, which one of those looks like you only need to do partial fractions on? The second one. Because we all can integrate 1. All right. So we see now that we got to do the partial fractions on that second bit. So we'll set up the recipe. Okay. So let's do this in blue here. Okay. So set up the recipe. X plus 1 over x times x minus 1. We factor the denominator. Okay. That's equal to distinct linear factors. So a over x plus b over x minus 1. Okay. Now we clear the fractions. Okay. Do another color change here. So we clear the fractions like always. X plus 1 equals a times x minus 1 plus b times x. All right. Cover-up method or equate coefficients, however you like, okay? However you like. Okay, you should be able to see it, but let's do the equating coefficients here. So lazy value, if x is equal to 1, the right, we get 2 equals, well, 1 minus 1 is 0. A term vanishes. And 1 times b is just b. Okay, there we go. And now, if x is equal to 0, the other lazy value, on the left I get 1, and on the right I get, well, negative a. That means a is equal to negative 1. This worked out nicely. All right. Let's actually go ahead and move this off to the side somewhere. Okay. So I have a bit more room for my integral. There we go. All right. We are almost done. Okay, take a look at that. We're almost done here. So let's write down the recipe, okay, from the decomposition here. So 1 plus, okay, a was -1, so I'll just write a -1 over x, and then plus 2 over x minus 1 dx, okay. And, well, what do we have here? Integral of 1 is x. Integral of -1 over x is minus log absolute x. And then plus 2 log absolute x minus 1 plus a constant. Just because you see a fraction doesn't mean you have to do partial fractions. You see how this worked out, right? We had to do long division, okay? We're almost there. One more to go. One more to go, I promise you, okay? Again, if it's not bottom heavy, you got to use long division, okay? This one was equal heavy. Okay, same thing. If it's top heavy, you have to use long division. All right, one more. Hey, I said top heavy, right? This one's top heavy, okay? So we have to use long division. So top heavy means long divide. All right, so we go ahead and set that up. So it's x cubed divided by x squared plus 1. All right, we look at the highest degree terms first, okay? So x squared, excuse me, x cubed divided by x squared, that's just x, okay? X times x squared is x cubed. And then x times 1 is just x. Okay, we subtract. X cubed minus x cubed is 0. Okay, I have a 0 here, and then I get 0 minus x is negative x. And do I have anything else? Well, no, okay? Because x has degree less than, well, I should say negative x has a smaller degree than x squared plus 1. So take a look at what I got here. This integral here, let's rewrite it. Integral from 0 to 1 of x cubed over x squared plus 1 dx. That's equal to, we'll take a look here. The quotient is just x on the top there, okay? And then minus x over x squared plus 1 dx. Take a look, right? I have a polynomial, right? I just have the x there. That's the first term. But the second term, let's lean in real close here. The second term, okay. Well, I see a sum of squares, right? That's an irreducible. There's no partial fractions really to be done here because that's the only factor. So you can go back to the C and say patterns, right? You can think, right, x equals tangent y, okay? Or think simpler, right? We already did an integral like this one before, right? X over x squared plus 1. Isn't that the same as that one? Just without the 2, right? We're using the same result here, okay? Again, u sub. So go back to this one. Okay, so go back to number 6 here. Okay, so this is similar to number 6 here. Okay, so I'll kind of skirt the result since we already have it, okay? Integral of x, that's going to be 1/2 x squared. And then if we use the result from number 6, okay, except we're off by a factor of 2, so we got to divide by 2. 1/2 log of, whoops, that should be from 0 to 1, okay? 1/2 log of 1 plus x squared. Between 1 and 0. Guys, this is it. We're done. Okay, it's late. I'm tired. So plug in 1 here. So we get 1/2 times 1 squared, which is just a half, minus half of log of 1 plus 1, that's 2. And then minus, we'll take a look here. 0 squared is 0. 0 times anything is 0. 0 squared is 0, plus 1 is 1, but what's the log of 1? The log of 1 is 0. And 0 times anything is 0. Okay, remember here, log of 1 is equal to 0. Okay. So if you like, keep this answer because you're done. If you like, okay, you can factor out the 1/2. Okay, you can factor out the 1/2. You can also write 1/2 of 1 minus log 2. Okay, there you go. Just because you see a fraction doesn't mean you have to do partial fractions, okay? So top heavy means you long divide, okay? Top heavy means you long divide. Equal heavy means you long divide. Once you have everything as bottom heavy, that means you do partial fractions. Okay, follow the recipe, use the method, okay, and then everything falls out. Okay, so we saw everything here, all right? And so this concludes our partial fractions adventure. Okay, now you basically have the most basic integral techniques typically learned in Calculus 2. There are more techniques out there, but beyond the scope of this class, okay, you can discover, you can play around, see what else you can find. But now we have everything. We have U substitution, parts, partial fractions, okay? Don't get those two confused, right? Integration by parts and partial fractions are two different things, even though they both have the word part in there. We also have the family of trig integrals and the trig substitutions. And so hopefully, with enough practice, you'll be able to spot which one to use. So I encourage you, okay, to go ahead and look at those exercises and see what you need to do. All right? Practice makes permanence, okay? And repetition legitimizes, okay? Repetition legitimizes. I'll see you in the next one.